Good afternoon, everybody. Just waiting for a few stragglers to trickle in, but we will get underway in a very short period of time. Pauline, I know you're there. If you can give me a thumbs up just to make sure that you can hear me. Okay, excellent. And everyone should be able to see the splash screen. So, Pauline, hopefully that splash screen is visible to you as well. Fantastic. So I think we've probably got most people in that we expect to have in. What I'll do is just ask everyone to mute themselves if possible, otherwise to keep the background noise down. We are recording today, and this will go up on our YouTube website, so it will be available later on for viewing. For those of you that haven't been here before, this is another one in our series of seminars offered by the Trusted Autonomous Systems Defence CRC. Most of you should know what we do in the CRC, but for those that don't, we're focused on delivering solutions for defence that exploit autonomy to enhance capability outcomes. And our website has a general description of what we do and some of the projects we work on. But today, we're here to hear from one of our fellows, Associate Professor Pauline Pounds. We have 4 fellows with a centre, all undertaking novel and groundbreaking research in the area of autonomy. And this is the second seminar from one of our fellows. So I'd like to welcome Associate Professor Pounds to this seminar and thank her very much for providing it. Just to give you a little bit of background before we launch in, the seminars are semi-technical in nature, but should be digestible to anybody who is reasonably versed in the field of autonomy. We will have a session for questions at the end, so please use the chat room to record your questions, and I will curate them at the end. For those that don't know me, I'm Simon Ng. I'm the Chief Engineer for the Trusted Autonomous Systems Defence CRC. So it's my great pleasure to host the meeting. And with that, what we'll do is kick off. So today, Pauline's going to talk to us about a rather cleverly titled talk, Stupid Solutions to Complex Problems. But let me tell you a little bit about Pauline before we go any further. Pauline's been working with UAVs since about 2002, so almost 20 years now. She did her PhD at ANU in 2008 in robotics and a postdoc at Yale University in the United States between 2009 and 2011. And she co-founded the UQ Robotics Lab, where she still works, in 2012. Pauline's undertaken foundational research in multi-rotor robotics, aerodynamics, and she's a pioneer in the field. And in addition to that, of course, she has founded or is a co-founder of a company worth approximately $90 million. The company is Oleris, and I hope I pronounced that correctly, Pauline. And so not only is Pauline an excellent academic, but she's also an entrepreneur. And I think that's one of the things that really adds value to what Pauline does. She has 12 patents to her name and 1 pending. But most importantly, she is the recipient of a number of awards, including the 2013 Discovery Early Career Researcher Award, the 2015 Science Young Tall Poppy Award, and she was a top 40 finalist, a top 5 under 40 finalist in the ABC RN competition. But most recently, just this year, in fact, Pauline won the Batteran Medal for Engineering Excellence. I've put a link up to the video associated with that medal on the splash page here. So hopefully if you have a moment, just jot it down. And I encourage you to look at it. It's a great video and a great introduction to Pauline and what she's capable of. So without further ado, what I'm going to do is to hand over to Pauline. I will switch the spotlight video, so hopefully you'll all be able to see Pauline. And I will mute myself and away you go, Pauline. Thanks very much.
Brilliant. I'll just share my screen and I'll jump in. Let's see. Hopefully this will all work. Excellent. All right. Yep, thumbs up. So I think we're good to go. So I'm hoping this is the only time in my career that I'll have a slide with a title written in Comic Sans. And I promise you this is the only place the Comic Sans shows up in the presentation. So if you're into typography, please don't be insulted. But I want to talk to you about sort of the antithesis of what most of us think about when we talk about autonomous systems, which is stupid solutions to complex problems, as opposed to smart solutions to complex problems. And I'll talk a little bit about that. But before I get into that, I want to throw you into a scary scenario. You and your team, you're out in the field and there's a dark room that you need to clear. Somewhere in this room, there's an excellent chance that there might be a man with a gun. In fact, there might be multiple people with a gun. It's dark inside and you don't know what's there. You don't know where they are. So the approach that we would all sort of immediately come to is, let's send a drone inside. Excellent choice, one that I certainly prefer myself. But this is a more complicated scenario than some of the sanitized approaches we may be used to. For instance, there might be obstacles and cover that are hiding our targets. There might be walls. There might be doorways to navigate. There might be branching corridors that we have to deal with. We might have furniture and other obstacles in the space. And if it's a tactical scenario, there might be smoke or gas or some sort of particulate obstruction. And all of this becomes very difficult, very fast. Right? We have a complex, compact, sensor-denied environment. There's no light, there's limited vision, there's no map, there's no GPS, and you have very little time to think. You're not just dealing with a room that needs to be mapped. You have an alert and non-complacent adversary. Your opponents will actively respond to try and stop your drone incursion. So your unmanned system has to be both smart, capable, and prompt. So the intelligent approach to this, of course, is to festoon sensors onto our drone. Plurality of sensors, scanning LiDARs for mapping, cameras and object identification, radars for being able to navigate through our smoke and particulate obstacles. And all of that requires some heavy-duty computation. So multiple core processors with dedicated pipelines for computer vision, and tracking, and SLAM, and person recognition for when we find one. And this requires a seriously capable platform. This is going to be heavy and it's going to be expensive. And with apologies to my very good friends at Emerson, you might think it would look a little bit like this. This is a fairly large and, quite a high dollar figure drone, but it's extremely capable. It can navigate autonomously. It can give you exquisite maps that tell you everything you ever wanted to know. The problem with this, however, is that even if you have an intensely capable platform like this, it can still potentially be defeated by a hippie bead curtain because your LiDAR didn't pick it up especially well. You weren't sure if it was a fog or if it was some sort of cable or if it was a clear pathway that you totally didn't detect. And now your $200,000, $250,000 platform has been brought low by something you can buy for $2 at the local op shop. And that's not a great look, and it's very expensive to learn that in the field. So as technical people, we like to think that we can solve all problems just by building really smart robots. And that's a great approach to take in general, right? It's safer, it's faster, it's less expensive and less risky than putting a human into that room. Fantastic. And there's sort of a bit of a conceit that we have that more intelligence equals more better. But intelligence has drawbacks too. It's expensive to design, build, implement, and operate systems with high intelligence. Computer systems are heavy and they're fragile. They very rarely like to be dropped. And they're also potentially brittle to unforeseen circumstances. If you haven't programmed it in before the mission starts, it's very difficult to build a system that will be flexible and adaptable on the fly. And that's one of these key topics that robotics is addressing as a field these days. So, okay, well, this is a really hard scenario. And we might be tempted to say, cool, some problems you just can't solve, right? Case closed. Great. See you at the coffee break. It would be a really short talk if I thought that was the case. So I'm going to switch it up a little bit, and I'm going to introduce you to a friend of mine. And it is humanity's deadliest predator, because we kind of know that there's a solution to this problem. And here he is, there in the center of your screen. I don't know if you can see him. We'll draw a line around him there. There he is. You might be familiar with him, in fact. He's 100,000 neurons. He's killed billions of humans. In fact, by some reckoning, mosquitoes have killed about half the humans who've ever lived. through malaria viruses and parasites, which is a heck of a thing for a flying platform. I mean, that's really good value for money. But no one would say that a flying insect is smart. And I mean, even at the low end, our good friend, the Aedes mosquito, he's 100,000 neurons. Slightly more complex than him, but with the same number of neurons roughly, is Drosophila, which is the fruit fly, and also happens to be the most complex connectome that science has completely mapped. Slightly more complex again, although I haven't been able to find an exact strict number on this one, we have the common housefly, which is 250,000 neurons. But the intellectual heavyweight of all of these flying insects is, of course, the honeybee, with just shy of 1 million neurons. But by no measure would you say that the honeybee is a smart platform, not compared to humans. I mean, human beings, for reference, have about 86 billion neurons. So there's a bit of a step between the two. But some food for thought. Have you ever tried to swat a housefly and missed? I mean, your brain is massive compared to that of a housefly, and yet try as hard as you might, you just can't get the things. And I'll give you a hint, it's not because you didn't miss because you're physically incapable of doing it. A housefly typically flies at only about 7 kilometers per hour. That's a brisk walking pace, right? You can get there if you're on target. The answer as to why you can't is because not only are they extremely maneuverable in their flight patterns, they're also much faster at thinking and reacting than you are. Very fast sensing, very fast response. And they're cheap because flies are everywhere, much as we wish that they weren't. So it's a matter of time and response when it comes to swatting flies. And it makes me ask the big questions. How fast is fast when we're making decisions? So a bit of a cosmological thought here about how fast things happen. At the very, very far end of the scale, we have the fastest thing that really happens in the universe, which is things at the Planck time. That's the time it takes an object traveling the speed of light to go 1 Planck length. So very, very, very fast at 1 × 10⁻⁴. If we go down about 23 orders of magnitude, we have the fast response of protons rearranging within a nucleus. At 1 × 10⁻21, nuclear reactions happen at that scale. And it's mind-bogglingly quick. If we go down 2 orders of magnitude, about 100 times slower, we have electron interactions, which is the time that it takes for an electron to migrate to a neighboring atom within a matrix. And if we go 10 orders of magnitude slower than that, you get the fastest chemical reaction, which is a proton transfer within a hydroxyl reaction. And that's on the order of about 1 nanosecond. If we go down an order of magnitude, so 10 times slower, that's about the speed the standard microprocessor's instructions will run at. So about 100 megahertz on that scale. If you go down an order again, you get the time that it takes for a typical human neuron to fire. That's the time that it takes for the potential from one end of the neuron to migrate to the other end. And that's at 1 × 10⁻⁷. 10 times slower than that, we start to get to the speed of things that we're a little bit more familiar with. So fast mechanical actuators and resonances will happen at about 1 × 10⁻⁵. So that's about 10 kilohertz in speed. 10 times slower than that is about the speed of the fastest ever drone dynamic control loop. That's about 32 kilohertz that I've seen. That's 1 × 10⁻⁴. 10 times slower than that, you have the neuron refractory period. So this is the speed at which your brain is able to make changes in its internal state. And that's about 1 kilohertz. Your typical robotics dynamic control loop, so what you'd have in a standard drone that you're dealing with, is about 0.01 of a second. And that's about 100 hertz. And coincidentally, the speed at which the fly's brain is able to process and change its controls. 10 times slower than that, 0.1 of a second, is the fastest ever human reflex time. That's the time that it takes for a human to have a stimulus and then respond to it with a motor control response. And that brings us to the scale of human cognition speed at about 1 second. If you wanted to think or react or do something on the shorter scale that you're really able to do it, it ends up being about a second. About 10 times longer than that, if you really took the time to think through something, if you had to make a good decision and you knew that you were on the line, 10 seconds, orders of 10 seconds, maybe you'd stretch it out to a minute if you had to really think it through. but human reasoned decisions for an individual take place in about 10 seconds, order of magnitude. And as you go up from that, and you start bringing more humans into the loop, you start to have better decisions being made, but it's starting to take you longer. To have a small committee of, say, 10 humans, you're going to be taking somewhere like 2 minutes to get a consensus. And if you have anything like an organizational decision, where maybe you have 1,000 humans you're looping into the decision, then even just finding out what people think is going to take you an appreciable chunk of time. And at this point, it gets much more gray area because it depends on how humans organize themselves. But across about those 4 orders of magnitude, you'll get to the large-scale organizational responses, where perhaps you're now talking weeks before we can figure out what is the best decision for our organization, for our group of humans to make. So I want to highlight these 3 in the middle, because these are where cognitive agent responses as individuals with reasoned or basic reactions are occurring. And this is really the time scale that we think about when we think about how robots behave, how humans behave. We are very agent-based. As we go up to these higher end responses, we have collective responses made by multiple agents working together and exchanging information, and they are much, much slower. Down at the lower end, on the order of the physical interactions within the world, things that are subcognitive, where no deliberative or formal thought is being done, we have non-cognitive agent responses, and these are, of course, much faster. And there's a trade-off between speed here and quality, delegation, and consensus. We expect that many brains working together will make better decisions, but they're going to be so much slower doing it. Of course, just to give a sense of scale, at the high end of the temporal range, of course, if you have about a million googolplexes, you get to the heat death of the universe. I like to keep things in perspective, and I think at some time immediately after that, I'll probably clear my email inbox, get around to getting that done. But that's a long time to come. All right. So moving on from that, what I want you to take away from this is that in situations of life and death in the field, it's really the quick and the dead. And your reflexive actions are always going to be faster than deliberative actions, right? I have a saying, which is that physics is faster than thinking. So with this trade-off between making good decisions and bad decisions, you really are better off having an okay decision now than the perfect solution too late. So if you're going to take the time to think, you've got to make sure that the time you're spending is actually giving you something you can't just get from these physical responses, subcognitive responses. And it really makes you think, because if a brain the size of a pinhead can defeat the smartest brain on the planet, right, why would you even bother with being smart? So I like to think of these non-cognitive behaviors as being a type of intelligence on their own, because doing the right thing at the right time is really the crux of intelligence, I think, right? And defining intelligence is one of these difficult things in of itself. How do you define it? Is it knowledge? Is it cognition, reasoning, understanding, or aptitude? And I like to quote Forrest Gump here and say, stupid is as stupid does. If you can have a system that's non-cognitive and still able to make good, fast decisions that outperform those of a smart system, well, I would argue your system is more intelligent. So I would like to dare you to be stupid. Wonderful things are happening at the not smart end of the scale. And I'd like to challenge the assertion that more brains equals more better. If you can have something that does the job faster and almost as well without all of the cost and the attendant overheads, I think that's a better approach to take. So I'd like to give you some examples of the systems that I'm developing that sort of encapsulate the style of thinking, of focusing on the physical end of the intelligence embodiment. So some examples of this are contact whiskers for measuring the environment around you, rotor sensors for measuring velocity of aircraft through the air, disposable drones that are made out of integrated circuit material, and just a little bit of a bonus topic at the end, bipedal locomotion, where we solve a difficult, complex embodiment problem by simplifying everything down to its elements. So I'll go through them one at a time. So I'm going to start with my whiskers, contact and pre-contact sensors. So I like to describing whiskers as being reaching out and touching someone without necessarily having to be close to them. And contact proximity sensing is absolutely critical for robots moving through an actual physical environment. If you're in a cramped and cluttered environment, contact with something may result in a risk to the robot, right? And there's lots of natural examples of autonomous systems, if you will, that are using whiskers to do things like navigating through compact spaces, finding prey, sensing vibrations of potential adversaries or food, using whiskers to measure the velocity of an animal through the water, and even much more obscure things like measuring the angular velocity of a flying insect with a specialized type of whisker called the haltere. And so for drones, we're very interested in using these capabilities because they give us a way of getting fast, early sensing about a potential contact when that contact force will be low, rather than during a hard contact where the contact forces may be high and damaging. So our goal is to navigate our microscale aircraft, about a 20-gram platform, through these dark, dusty, cluttered environments where heavier sensors are simply not going to be a feasible approach. So if we succeeded in it, it might look a little bit like this, right? It would be nice if we had that capability of being able to contact devices, get us contact surfaces, get a measurement back from our device, giving us orientation, giving us relative contact force. And it would be great if we could do that as a complete array of sensors that would give us not just an individual measurement, but actually a collective force flow field for the environment that we're in. It'd be even better if we could have some kind of visual feedback to the user that we'd be able to make some sense of. Of course, interpreting that information for a robot is an additional task on top of that. So that seems a bit unrealistic, but we'll give it a go. Okay. So how would we build something like that? Well, first of all, you need to measure force somehow. And using sensors that are able to measure forces can be an excellent way of capturing that information. But the problem is, how do you actually translate a physical contact with an environment into an electrical signal that you can measure? And this has been a topic of study for roboticists all the way back from the 70s. But some very clever people at Harvard University, working with Rob Howe, hit on the reality that force times area is equal to pressure. We already have really good sensors for measuring pressure, and they're called barometers. And in fact, we use them in drones all the time to measure altitude. So they figured, why don't we just take some of these sensors and see if we can turn them into a force sensing device? It was a great idea. So we took that idea, realizing that they were onto something, and we ran it to its logical conclusion, basically. We got a very small MEMS die. Rather than just being a barometer, we exposed the die itself and embedded that within a flexible medium. So here you can see a Bosch BMP 2080, 280 MEMS barometer. You see the little tiny green thing in the center there is the pressure transducer itself, and it's gold wire bonded to a circuit board material underneath it that gets soldered to the rest of your circuit. Normally these things come with a little protective housing, but we've removed that. And they are really tiny. They're on the order of about 2 millimeters, 2.5 millimeters aside. So if we take a whole bunch of these guys, we can build arrays of these sensing devices. And that way we get multiple measurements that are able to extract more information. So by arranging them into triangles and bonding a rigid plate into the center, we can basically build a directional load cell. In this case, you can see we've got 4 triangles of these three sensors in tripod configurations. They are assembled in a laser cut acrylic potting jig, then they are filled with a polyurethane material, and we glue the laser cut load plates on top of the scaffold, so everything is nicely aligned. Then we can cut them free when we're done, and hey presto, your sensor's ready. To have some whiskers, we needed to come up with a way of fabricating easily controlled flexible polymer material that we could bond to our load cells and have it multiple different lengths that we could control. And it's important to control not just the length, but also the thickness of the material. And our solution for this was to modify a 3D printer to act as a bit of a taffy-pull machine for those who are familiar with pulling taffy, where we put a dollop of hot ABS plastic on the load plate and then draw the head away from the surface. And that causes the plastic to stretch out and become thinner and finer as it moves away from the base. And with this way, we're able to get very repeatably 0.4 millimeter thick fibers. Now those little load cells are great, but to get the most out of them, you really want your fiber to be acting in a way that's going to act as an amplifier. So our configuration is to put that fiber right in the middle of our tripod configuration. Each of our pressure elements is able to measure really minute forces, but we can always increase its sensitivity by making the whisker longer. So the way that works is we have our MEMS pressure transducer inside the potted polyurethane material. The encapsulation is about 1.5 millimeters thick. That's all loaded onto a circuit board, itself about 1 millimeter thick. There's a microcontroller underneath that takes all the signals and does the processing. And there's a load plate that sits on top. Our whiskers will be about 40 to 150 millimeters long. And so when we add forces to the tip of that whisker, it will translate that load into a pair of force moment couples acting on the load plate. Since we know that the displacement of the fiber from the center is about 4 millimeters, and we have, say, a 40 millimeter long whisker, that gives us about a 10 times transmitted force coupling. Longer whiskers will give you higher force readings for smaller applied forces. All right. Now, these fibers wouldn't be much good if they just contacted something once and broke, so we decided to torture test them. We've tested them on a special machine we configured just for doing this type of testing, where we've basically taken our fibers to 1 million cycles, so 10 to the 6, of just poking the fiber over and over and over and over. So how well do they work? Got my video working there on the left. So here we're measuring the values we get back from our sensor pressure elements with respect to the applied force that we read through a precision diamond scale. And it's difficult to convey how small and fiddly this all was to set up. The forces, the scale, the sensors are all very quite small. And the takeaway from this plot is that it's quite linear. So as you apply more force, you get more value on your sensor reading. And as you change the point along the fiber where you contact, you're able to change the relative scaling. So you can see in the gray there, that's out at the tip. You're measuring very small contact forces and getting larger values, but the resolution is quite high. By the time you're reading closer to the root with the blue line, you're getting very large forces being applied on the scale of millinewtons of force, but you're still getting values that don't saturate the sensor. So we can use these sensors to measure the small forces acting on the fibers as they move through the air. This is something very important for our application with drones. So we've implemented a whirl tower, which is just a rotating swing arm that circles around with our whiskers out there on the tip. And they're moving at about 6 meters per second. And you can see as we speed up our sensors, the linear trend of the tangential tip velocity is represented by the blue line of the tuned sensor values we're getting back. And it's very interesting that there appears to be a superimposed sinusoid on top of it. And we believe that's because we actually mounted our sensors slightly crooked, and the weight of the whiskers flopping from one side and back is being superimposed on top of that measurement. And you can see that the dips of all of those cycles line up with the swing arm going past pi degrees. So we think we could calibrate that out and we get a smaller oscillation. But it's really interesting to see we're actually measuring the mass of our own minute fibers as much as we're measuring air. But overall, the trend is nice and linear. These things are also sufficiently sensitive that we can do some interesting, what I would call a party trick, which is if we set our whisker up and have it cycle around and swing past our fiber, that swing arm now has a load plate on it. And when the bow wave of air being pushed ahead of the fiber strikes the fiber, it will read a deflection in force. I'm going to play that again. So here it comes, and even before it contacts, it reads the threshold value and turns on its light. And it can measure that incoming contact at about 0.063 seconds before it hits. And that's fast enough for your drone to take some sort of evasive action or to apply a safety mechanism. So this is just a very first attempt at it. We think we can do better. But I think it's kind of interesting to see that as a proof of concept, we're able to actually measure contacts without contacting anything at all. So how would we use this? Well, proximity contacts of actual touching objects in the environment, pre-contact sensing, and flow fields. That's a whole bunch of information that you can then pass back to a pilot or process through an autopilot in order to do obstacle avoidance. And that's the approach I'm taking to some of the work that I'm doing with the fellowship with TAS. So it's good value for money as well. It's only $30 for these tiny little systems. They're not very difficult to put together, and there's not a lot of meat. So at 4.3 grams, even the smallest drone is going to find that pretty easy to carry around. And at $30, that gets you 4 of these sensitive whiskers. It gives you USB, UART interface measurements at 150 hertz. You're getting 13 discrete sensor measurements, the 12 of the tripods plus an extra one for a thermal calibration. And you could expand these to massive arrays of thousands of these modules. Basically, you're limited only by what can be supported by the USB interface. So you can coat your whole house with them, or perhaps your jet trainer if you wanted to measure incipient stall on the surface of your wing so that your pilots in training can be informed that they need to correct before they actually put the aircraft into a dangerous configuration. Or you could put them all over your submarine. And that's pretty important if you want to be quiet, if you want to navigate in turbulent waters and you don't know which way you're being moved. Being able to capture that information with a high degree of precision is something that no one has the capability of doing at the moment. All right, moving on from there, I want to talk about rotor force sensors, which are a very similar concept, trying to do a similar task, but using a very different approach to how you understand the forces in the environment. So people who work in drone flight control will be aware that the fundamental task of any drone is controlling your position, your velocity, and your acceleration. Everything else you do in terms of your mission or your higher order operations depend upon your ability to keep yourself on trajectory. That requires you to be aware of things like gust rejections, things like wind acting on your aircraft to push you off course. And if you can't do that, it's not very difficult to go from a meter away from a building to being against that building and in pieces on the ground. It happens very fast. So the gold standard, the state of the art for aircraft navigation like this is what I call the big pink cheating room. The big pink cheating room uses a whole bunch of these beautiful IR cameras that just flood the area in this specially structured light that can be captured by an array of receiving elements that are then able to take reflections from optical markers, put on top of your aircraft, and turn them into a spatial estimate of your position within that volume. From that, you can get velocity. From that, you can get acceleration. And it's very, very fast at about 1 kilohertz, and it's very, very accurate. And really, it's the ground truth for any experiment you do with this. And that's fantastic, except that it doesn't work outdoors because we are defeated by our old adversary, the sun. It turns out the sun is an enormous infrared transmitter. And if you have a sensing technology that's based on infrared light, you're going to struggle anytime that you aren't indoors or under heavy cloud or at night. So how do we work around this? It's great for fancy YouTube videos, but most of what we want to do is outdoors and very often in the day. And unfortunately, there's really no good alternatives. There's no what I call universal sensor. GPS is great for getting you position, but it's slow and it's a little bit imprecise depending on what configurations you have and how much you're prepared to pay. And it's also unreliable because if you're flying in urban canyons or if you're flying under heavy cloud, you're very quickly going to run into situations where you're just losing your lock entirely. Pitot tubes, which are used by manned aircraft, are terrific for high velocities, and they are a standard quiver in the tool set of pretty much all aircraft designers, but they're pretty much useless around hover where your velocities are low. And inertial measurement units, dead reckoning, inertial navigation systems, they're really good at capturing acceleration, but their drift is still pretty poor unless you spend a ton of money and buy a reasonably large fog sensor to put on it. Fiber optic gyros or other sort of ring laser gyros are very capable, but they're a little bit outside the domain of what micro miniature drones are capable of carrying. Well, all right. There is a relationship we can use though. If we have position, we can differentiate for velocity. If we have velocity, we can integrate for position. If we have acceleration, we can integrate for velocity. If we have velocity, we can differentiate for acceleration. So really, if we have velocity, we can get both of those with only one dynamic order step. What we want is a velocity sensor, I think. What if we exploit aerodynamics itself? So when you have an aircraft in hover, you have your rotor that provides thrust that keeps the aircraft in the air. If we have a lateral velocity through the air is going to push back against the rotor. And we know from aerodynamics models that have been developed for multi-rotors that there is an equation that links the lateral force acting on a rotor to a bunch of parameters based on our thrust and based on our translational velocity. Well, if we could measure that lateral rotor force, we could back out that oncoming wind. So what if we put a mounting system on our motor? That way, if we have a displacement from the rotor head to our mounting system, when we apply a force at the rotor from the rotor thrust, we're going to get a force couple back onto that mounting point. And at this point, this probably looks very familiar to you, because it's basically the same thing as what we did with our whiskers, except this time we've put a motor on top and put a rotating unit on it. So there's our MEMS barometers potted in a soft polyurethane, but this time they're running at a much faster speed. They're about 1 kilohertz each. And they're configured in such a way so that the thrust is being generated vertically, and we're measuring couples across the lateral and longitudinal axis of the aircraft. So we can bench test this load cell that we've developed, and we've gotten a JR3 load cell, which is about a $5,000 unit, and we've put on a long swing arm with our motor on the end, and we've put a test load at the point where the rotor would be. And we've just increased our test load by filling a cup with water. The length of the lever arm is configured so that the relative torque scales of the two devices will be within the dynamic range of those units. And this graph on the right is not actually a single line, it's actually 2 lines. One is the measurement coming from our sensor unit, and one is coming from the JR3. And as you can see, they're practically spot on. So we're basically reproducing the capabilities of a $5,000 sensor with our little tiny rotor unit. If we turn that onto our swing arm rig again, and this time we bring our rotor up to speed, so we're acting as an aerodynamic amplifier of sorts. The more thrust we produce, the greater the signal will be translated into the lateral force component of our sensor. If we spin our rotor arm around at about 0.53 meters per second, you can see very clearly in the direction that we've mounted it, you can see the signal will increase. And that's that big step in green. But what's also very interesting is that when you start changing your rotor velocities in translation, you also read a change in the force being generated vertically by the rotor. And we can actually measure that too in that red line. There's a very small dip. And to us as aerodynamicists, that's super exciting. In fact, it's so sensitive that we've kept having problems, because if the air conditioning in the room was turned on, as it would go around a complete circle again, our old friend, the sinusoidal superposition, would show up once more. And we said, aha, we know what this is, but what on earth is this cross calibration? We knew that our aircraft was totally level. We knew that our swing arm was properly configured. And we knew that sometimes it just didn't show up and everything was clean. And then we realized that on the days the air conditioner was on, we had the problem. When it wasn't on, it went away. And we realized that, again, the frequency of rotations was matching the sinusoidal period. And as soon as we turned the air conditioner off, we knew that we'd had it solved. Now, the air conditioning draft in our office is very, very minute. We couldn't even tell unless we actually inspected the panel, but this is capable of detecting it. So we're very interested in the linearity of our measurements. So we know the applied lateral velocity from the swing arm times its swing arm speed times its arm length. And from that, we compare against the sensor torque reading that we're getting. By putting that into a rotor model, out will pop the translational velocity as an estimate. Brilliant, let's build it into an aircraft, because it's no interest to me to have it sitting on a shelf or on a swing arm. I want to see it actually fly. So the data we get out of it is not just data from a single rotor. Instead, we have these sensors on every single rotor of the aircraft, and they're connected together by a small Raspberry Pi module that collates their information and runs the estimator algorithm. We have 16 sensors that we devolve into couples of 2 and then a vertical velocity. So you can think that X is being measured by 2 force couples, Y is being measured by 2 force couples, and together they give you a Z component. So 4 times 3 measurements per rotor gives you 12 parameters. We have a 6DOF dynamical model for roll, pitch, yaw, X, Y, and Z. So we have a 12 by 6 matrix pseudo inversion. For those of you playing at home, you can't do that unless you make some assumptions about how your pseudo-inverse will happen. But if you turn the math around very carefully and make some assumptions about the characterization of that, it'll work. Trust me on this one. And so what we get is we get a very interesting set of data. It's a little bit hard to see because it's made in a lighter ghosted color on these plots, but you'll see all of the sensors being measured in a particular velocity direction, and it looks very, very noisy. But what's interesting is that if you take the pairs and devolve them through this algorithm we've developed, you get a very, very smooth measurement out for the collective behavior. And so for translational velocity, all of your systems will be able to contribute to that. All 4 of your sensors will contribute to your translational estimate. And from that, you can see that measuring it against a ground truth measurement from our optical system that we have in our lab, it's an OptiTrack system, it's a $40,000 piece of equipment, we're pretty much spot on. And the places where it begins to break down is here at the end of our tests. You can see there's a bit of a digression, but we start entering ground effect and our aerodynamics model begins to change. Even under pretty extreme maneuvering, in this case, we have our aircraft flying in very fast circles, doing a complete loop in about 5 seconds. Right at the very extremes of those motions, we get a bit more digression. And again, we believe that's because our aerodynamic model is incomplete, but additional aerodynamic models will probably shore that up. And once again, entering ground effect, you can see we have a bit of departure from our model. Prior to that, it's very well characterized. And if you plot all of the measurements that we've taken in the 3 preceding experiments I've shown you, and we plot it against the known ground truth velocity versus our estimated velocity for the set of the aircraft, we get a very nice linear trend, except for one little outlier there, which we think was a data bus error. So it's pretty competitive against your $40,000 indoor optical tracking system, which I think is good value for money because it costs only about $200 to build a complete array of 4 of these devices for mounting onto a drone. And that's 40 grams as a mass burden for your platform. And whether you're flying indoors, outdoors, over water, over ground, day or night, in smoke or in fog, these systems will still work because they're attached to the fundamental mechanism by which your aircraft will fly. And with 1 kilohertz measurements, you're actually able to get a higher order of feedback than you would through other systems. So we're running out a little bit of time because we started a bit late. So I'm going to try and step it up a bit so we've got time for questions at the end. I'm going to quickly step through disposable drones. We're very interested in having a mechanism for building drones cheaper because we wanted to throw them into bushfires where they might get burned up. Parachutes would have been too expensive and they were very fiddly to produce. And it boiled down to what material we'd like to use. So we needed something that would be suitable for electronics and amenable to making aerodynamic shapes out of, but it couldn't be very expensive. It had to be cost effective in mass volumes. We had some great inspiration from other colleagues of mine at Berkeley and at Harvard who were producing folded origami robot shapes. I thought, we could do that. And so we hit upon polyimide, aka flex PCB, aka Kapton tape, aka God's tape, which was developed for the Apollo program where they coated the lunar lander with it. And people build complex circuits that are etched onto the substrate of the polyimide material. And this is great because you can build the circuit board into the aerodynamic shape. You can put your flight control, all of your sensors onto that mechanical structure, and it will just work. You don't have to do anything more to it. And in this case, we've built an example, which is a fully passive rotary wing aircraft that we can throw out the back of a drone, drop over an area, and get tropospheric measurements. And it's kind of neat. This video might be a little loud. This is a view of our sensors descending, and it looks surprisingly well. Because they're fully passive, there's nothing to go wrong. There's no range to have to worry about. It's way on the range. All right. And you can get some interesting wide area data from that. Here we built up a wind map around an environment out at CSIRO's Pull and Veil UAV test range. And we're able to track where updrafts were occurring, where the wind flow was changing over the period of the experiments that we were performing. And you're not just limited, of course, to fully passive aircraft. You can build in steering, you can build in propulsion if you really want. It just comes at extra cost. So you can imagine you could build a system like this, a super low-cost UAV with an onboard GPS module that could steer your aircraft to particular predetermined locations. And again, good value for money. We care a lot about that since we're building lots of these systems. If we can build them for less than $10 per unit, we could build 1,000 $10 drones instead of one $10,000 drone. And we can even make them cheaper by using biodegradable material like paper. We can have self-immolating materials like paper or shredded cardboard that could catch fire when we're done with them. Presumably not if you're doing environmental monitoring for bushfire. You probably don't want to start fires then. So if we combined all these technologies we've just talked about, we start to get something that looks a little bit like our old friend. So we could have a super cheap, highly integrated, drift compensated, fast reacting micro-miniature disposable drone. We could give it some passive embodied intelligence for avoiding obstacles by sensing contacts before they occur, using whiskers in the environment by measuring their wind speed. And we could do something neat like doing what a mosquito does and putting CO2 sensing or thermal sensing and use that to detect humans in an environment. And then we could play an interesting trick. Let's go back to our dark room. Now, instead of one UAV, we have a whole fleet of UAVs. We can have thermal sensors so that when they get close to a human, they can measure them by body heat, or we could have CO2 sensors to measure their proximity by gas cloud sensing, measuring the gradient to fly right to them. And now we can have them fly all sorts of trajectories into that space. And when they actually find a human, we could even have them cling to them and start emitting a beacon. And now your guys in the field will be able to say, hey, there's a noise coming from that guy over there. There's a guy there. Okay, we can do something about that now. And so that way you're not going to be surprised when you actually enter the room. So just with a little time I've got left, I'll breeze through it by bipedal locomotion. We want to build leg robots. This is the dream. Aerial robots are great, but they're no substitute for boots on the ground. If you want to carry heavy payloads and have long endurance and keep pace with humans in human-built environments, you really can't beat legged robots. The world's constructed around bipeds because we're bipeds. So we would like to build these for a variety of applications to go in places where either drones can't go or where they don't have the endurance to compete. You might ask, isn't this a solved problem? Boston Dynamics has built a long and fascinating career by being mean to walking robots, kicking them and hitting them with hockey sticks. And you might be inclined to think this problem's done. But if you paid attention thus far, you'll probably understand where I'm going with this. Using legs to do that balancing control winds up being expensive. You have to have very capable sensors, very capable actuators, and it becomes a prohibitive thing to build large numbers of these devices. So eliminate the expensive bits, right? Drones fly by using rotor aerodynamic torques and controls to stabilize themselves in the air and reject disturbances. What if we did something very similar? What if we used a similar approach to have torques and forces and then just treat the contact with the environment as being a disturbance to eliminate? So our approach to that is to build a high-speed gyroscope into the robot that we have on a pan tilt rig to be able to apply torques in order to stabilize the platform. So we can make that much, much cheaper because now we've thrown away all the hard bits. I'm going to step past that video and bring you to this video just because we're running out of time. And here you can see it balancing itself. We can be mean to it by poking it. We can give it bias loads. So now it's soft balance and it will correct automatically. If we take it away, it'll balance automatically. And this is all being done with the same type of flight control system that's built into conventional drones you buy off the shelf today. We can even change the ground structure on it so we can apply a tilt both laterally and longitudinally, and we can apply an earthquake, which will give it some additional forces entering through the feet. And I'm very proud of that because Boston Dynamics struggles at that task. We can walk on the spot, and we can even walk forward. At the moment, our walking speed is quite slow because we're being very careful. We need to make some changes to the feet, but it's become quite reliable. We can turn on the spot by applying a small little twist to the feet as we're walking in place. And so now we're at the point where we can basically drive it around as if it was a remote control car. All right. So that's just the tip of everything that I do. I build all sorts of strange flying platforms and oddballs, new weird things. So everything from flying hat racks to triangular quadrotors to power line inspection platforms to robots that grab objects and transport them. as well as safety systems. So if your robot's attacked by hot dogs, you can be safe. And with that, we are well and truly out of time. So I'm happy to take any questions.
Thanks, Pauline. I'll just put my video back on. Actually, it is on. Fantastic talk. Absolutely loved it. I love this work. I think embodiment is something that we tend to overlook in the AI space. I'm also a UAS, unmanned aerial systems person. I know how hard it is actually to get these systems to perform simple jobs. And so it's really exciting to see these extremely low-cost solutions to what are fundamentally challenging field robotics problems. I will open it up to the floor, but maybe just to kick things off, embodiment is certainly something that roboticists have exploited to solve basic problems like walking, for example. But where do you see the limits of these simple solutions to what are currently considered significant cognitive problems? And how would you know, how do you judge where those limits are when it comes to solving those sorts of problems?
So robotics is fundamentally the business of identifying structure and exploiting it. So if you have a physical system where there is a clear physical system that you can use, such as a drift velocity or contact of the environment or some other value like that, that you're able to measure through a sensor and derive a clear action as a result, it's a pretty clear case where embodiment's a good approach to take. Passive stability is a classic example where just the mathematics works for you and everything balances out. However, the problem becomes where your measurements may be ambiguous and it may take numerous measurements in order to extract the salient features required for you to understand that structure. And the classic problem here is telling the difference between a kitten and a puppy. You can find any number of dogs and cats out there that look surprisingly similar to one another. And if you needed to tell short of a DNA test, you actually have to know a bit about dogs and cats. For a robot, that requires contextual information that's very difficult to encapsulate, not only as a cognitive task, let alone as an embodied task. So cases where you have multiple measurements, multiple values, and contextual information driving your cognitive decision, I would say that those are not good examples of where embodiment could be useful. That's not to say that it's impossible. For instance, you could build a sensor that measures whether you're getting purrs or barks from your kitten or your puppy, but that would require a lot more information about the system than the sorts of things I'm talking about.
Thanks, Pauline. I do have a couple more questions, but I just want to give people on the floor a chance to ask those questions. We are coming up to 3 o'clock. So does anyone have any questions or comments indeed they'd like to make? Just unmute yourself, please. No, so look, I'll keep going with a couple more questions. The positioning, or I suppose velocity, position, acceleration sensors that you're talking about, one of the big challenges in military operations is maintaining an accurate position estimate and indeed an accurate velocity estimate over large distances when you're in environments where GPS and those sorts of things aren't effective. To what extent do you see those sensors as providing reliable long-term position information, assuming you took off from a known position, or do you see them much more as drift compensators, so only part of the solution for positional information?
So I see them as actually being a hybrid between what you've talked about. So one of the things that is very interesting about aerodynamics is that the objects around you in an environment actually interact with the air as much as they interact with an object. So if you understand how the flow fields around objects manifest, and you're able to put that into some sort of classifier or basic model within your system, you could use that to seed your localization solution. So for instance, if you know that you're going to get a recirculation close to a wall when you bring a rotor up close to it, when you start to see the particular characteristics of recirculation appearing within your rotor characterization matrix, you can then say, aha, I must be close to an obstacle. And I can use that information to find the boundary of that obstacle. I can use that to start building a topological map, perhaps not in absolute position, but at least within a connectivity type approach that would be very familiar to people who work in the SLAM field. If you employ additional sensors on top of that, such as your absolute velocity estimate in order to extract some sort of dead reckoning, then you can begin to piece together all of these values. And it's a little bit like feeling your way through the dark. You may not be able to see anything, but you can sort of measure the positions of things around you by where your hands are relative to you when you touch the walls or an obstacle or the staircase as you're going down to the bathroom in the night. So if you're able to capture that information in addition to your straight line velocity estimate, you can begin to piece it together. And ultimately, if we put any robot or even humans on a perfectly undifferentiated white flat plane, our sense of our absolute position would very quickly degenerate because we would have no salient features. This approach only works where you have landmarks that you could exploit for that kind of technique. Otherwise, things like GPS, if you're flying in clear air over long distances, there's a reason why it works so well. But if you don't have GPS and you're able to capture this kind of information and potentially other information like optical flow type things, you can use very basic sensors to do something similar. So I'm not going to say that it's a silver bullet equivalent to that kind of absolute value sensor for your position in the world, but it's a part of a toolbox that you can start to draw upon for these kinds of tasks.
Yeah, absolutely. And I mean, I think there are a whole range of indoor applications where these types of low-cost solutions are going to be central to effective robotics. I have one more question, and then I will again give people a chance to ask questions of their own. So you kind of hint at swarms in that last slide. How far away are you or are we, do you think, from the sorts of swarms that really you were hinting at, you know, whether something akin to a bee swarm or a swarm of mosquitoes? What problems remain to be solved for us to have that sort of small and many concept fielded?
So when people talk about swarms and swarm robotics, especially in the UAV field, they have a particular sense of what they want a swarm to do. They want it to fly like a group of locusts where there's this semi-organic meta-organism that's carrying on a task as if it were a single element made of many discrete components. And that requires communication between you and your neighbors. What's really interesting about things like locust swarms is that they don't have that communication except through their proximity and perhaps pheromones or some other proximal measurement they're able to make. Being able to measure the proximity of aircraft flying together is something that I think is certainly a near-term goal and something I'll be trying to do very soon. And once I have that, then having separation maintained within a swarm becomes basically the same thing as having ping pong balls bouncing off each other in a swirled up bit of air. It's just a physical phenomenon that occurs. But in our case, we have that barrier around us formed by our sensing envelope that we reject close contacts. But the meta-organismal approach of directed action by the group becomes much more difficult. And this is where we can take a cue from things like ants, where they use chemical trails in order to seed group behavior based on an individual that's able to make much more intelligent decisions based on information they already have. I found food, I know where my home is, I'll leave a scent trail back and all of my friends will come and exploit that knowledge. We can do something similar so that we don't have to build a very smart aircraft, but we can have a single, perhaps human piloted aircraft doing a task and then saying, hey, everyone follow me, and we all just follow that signal. In terms of having something that's got very low individual intelligence, but made cheaply such that we can have very large numbers of them, that I don't think is the challenge. The challenge is getting that meta-organismal autonomous behavior, which I think is something that has another step before that will happen. But I think we'll certainly have useful swarms of aircraft with high degrees of autonomy, but low degrees of intelligence long before we have that. And with something like the room clearing example I gave, you don't actually have to have collective intelligence. You just throw enough of these things into a doorway and they're going to bounce around until they find an exit or until they find your target. And the great thing is many, many aircraft can go at places where a single one can't get. simply by having the time through parallelization to explore all possible avenues. And there's very few systems on Earth that are fully robust to the point that there's no chink in the armor, no gap, no weak point. If you have enough elements, eventually something will get through. And we haven't really understood how that can be. Anyone who's ever been caught in a building during one of these enormous swarming events will be able to tell you there's no way to keep them out. They find a way. Replicating that capability just by making aircraft smaller and cheaper, I think, is a good way to get near-term value in that arena without having, communication necessarily.
Great answer, Pauline. And look, thank you again. I will open it up one more time. Is anyone else wanting to ask a question? Just a few seconds to give people a chance to speak up.
Also, if people want me to go back and go over some of the things I rushed through a little bit, I'm happy to do that too.
So we have a question actually from Jason, the CEO. What might it cost to build a bipedal of this kind that could operate reliably in a human environment?
It's an excellent question. And I'm going to respond with another question, which is, what do you mean by reliable? Because if you've ever gone out on icy steps walking outside of a building, say in the States, like at Yale, for instance, where it gets quite cold, I don't know a single human who hasn't slipped and fallen. So I'm going to immediately say, we have to accept that perfect is impossible. So then the question is, how good do you want? And I'm going to assert that what you really want is something that's as good as a human being would be. So not perfect, but pretty good. And then it's a question of, well, how big do you want? So I'm going to say that since you're saying human environment, we're thinking roughly human size. It all boils down to the actuators you buy. And at this point, it's not the quality of the actuators, it's the size of the actuator. I estimate that for a platform of human size, you're looking at something like $40,000 to $50,000 for a very basic system. And I think that actually competes very well with much, much simpler quadrupedal systems, which don't face anywhere near the level of complexity and dynamical control task that a biped does, which are on sale by Boston Dynamics for $75,000. I don't think that the Atlas robots are anywhere close to that in terms of how much they cost, even after they've been productized. So the fact that we can build something that's tens of thousands of dollars instead of hundreds of thousands of dollars is pretty cool. And if you know someone who's got tens of thousands of dollars who wants to help us build one, I'd love to talk to you. Ian has suggested spring-loaded short spikes on your shoes. Yeah. And absolutely, that's a thing you can do.
Yeah, great suggestion. Look, I will close it off there. We are a bit over time. Pauline, thank you very much for a really interesting talk. As a person who's spent the last 10 years in the robotics field specifically, I just love the stuff that you do and applaud it. Before everyone does dive off, what I will do is just bring up a flyer for our next talk. So bear with me for a moment. I'm going to take control, Pauline.
Yep, I'll stop sharing.
Yep. And I'm going to put this up just so people can see it. This, I think, is scheduled for the end of next month. Dr. Jessica Corte, who's another fellow for the Centre, and she is going to talk about technologies pipeline for enabling human-machine visual communication. So I encourage everyone to come along to that and circulate that around to people that might be interested. And with that, what I will do is call today to a close. Thank you to the audience and thank you to Pauline.
Thanks, everyone.
Pauline, we might just stay on for a moment.
Yeah, happy to.